Hello and welcome. Today, we're going to delve into a fascinating concept from the field of econophysics called the Darwinian selection equation for strategies. By the end of this walkthrough, you will be able to understand the components and meaning of this equation, which models how financial strategies evolve over time. Let's start by looking at the full equation. This equation might look intimidating at first, but our goal is to break it down piece by piece. It describes the change in popularity or market share of a given investment strategy over time. Essentially, it tells a story about competition and innovation in financial markets, drawing a powerful analogy to biological evolution. In this scene, our objective is to understand the left-hand side of the equation, which represents what we are trying to measure. Let's focus on the term on the left, d pi over dt. To understand this, we first need to know what pi sub I represents. The symbol pi, or pi sub I, stands for the proportion of total capital invested in a particular strategy, which we'll call strategy I. You can think of this as the strategy's market share. If pi is 0.1, it means 10% of all money in the market is using strategy I. So pi is simply the weight or popularity of strategy within the entire population of strategies. The d over dt part is a derivative from calculus, and it simply means the rate of change with respect to time. Putting it together, d pi over dt represents how fast the market share of strategy I is growing or shrinking. A positive value means the strategy is gaining popularity, while a negative value means it's losing favor. This entire equation is built to explain what causes this change. So we've now met our objective. We understand that the left side of the equation, d pi over dt, is the rate of change of a strategy's market share. Now let's explore what causes this change. Now let's tackle the first major term on the right-hand side. Our goal here is to understand the selection part of the equation, which is the core driver of competition. This entire expression represents the selection mechanism. It determines which strategies thrive and which ones fail based on their performance. Let's break it down further. First, let's look inside the brackets at the term pi sub I of p, x. This term, pi sub I of p, x, looks similar to our market share term, but it's a function. It represents the profitability or expected return of our specific strategy I. It depends on p, the distribution of all strategies in the market, and x, other external market variables like interest rates or volatility. In other words, a strategy's profitability isn't fixed. It depends on the overall market environment and what other traders are doing. Next, let's look at the second part inside the brackets, the summation term. This term calculates the average profitability across all strategies in the market. It does this by taking the profitability of every strategy J, which is pi sub j of p, grax trop x, and multiplying it by that strategy's market share, p sub j. Then, it sums them all up. This gives us a weighted average of how well all strategies are performing. It's the benchmark that every individual strategy is measured against. Now, let's look at the difference between these two parts. This subtraction calculates the excess profitability of strategy I. It answers the question, how much better or worse is my strategy performing compared to the market average? If this value is positive, our strategy is a winner. If it's negative, it's a loser. Finally, we multiply this excess profitability by the strategy's current market share, pi sub I. This means that the growth of a strategy is proportional to both its performance relative to the average and its current size. A highly profitable strategy with a large market share will grow much faster than a highly profitable but niche strategy. So we've achieved our goal for this scene. This entire first term is the survival of the fittest mechanism. It rewards strategies that outperform the average and penalizes those that underperform, with the effect being magnified by the strategy's current market share. Let's move to the final piece of the puzzle. In this scene, our objective is to understand the second term on the right-hand side, which represents innovation and randomness. This term is ETA times the gradient of h of page. It acts as a counterbalance to the pure selection we just discussed. It introduces diversity and exploration, much like genetic mutation in biology. Let's break it down, starting from the inside with h of p. H of p is the entropy function of the strategy distribution p. In this context, entropy is a measure of diversity or uncertainty. A high entropy means there are many different strategies being used with similar market shares. A low entropy means the market is dominated by just a few strategies. Think of it as a measure of how predictable the market is. High entropy means high diversity and low predictability. The symbol nabla-sub-p represents the gradient with respect to the strategy distribution. The gradient of entropy, h of p, is a vector that points in the direction that would most rapidly increase the diversity of strategies. This term acts as a force pushing the system away from concentration and towards more variety. It's the mathematical representation of innovation, random exploration, or the introduction of new ideas. Finally, we have the Greek letter eta. This is a small positive constant known as the learning rate or the intensity of innovation. It controls the strength of this random exploration. A higher eta means the market is more willing to explore new random strategies. A lower eta means the market relies more heavily on the proven performance of existing strategies. It's the knob that tunes the balance between exploitation of known good strategies and exploration for new ones. We have now met our objective for this scene. The term eta HOP represents a force for innovation and diversity, preventing the market from becoming stagnant and allowing for the discovery of new strategies, analogous to mutation in evolution. In our final scene, we will bring everything together to understand the complete story told by the Darwinian selection equation. The equation states that the change in a strategy's market share over time is the sum of two opposing forces. The first force is selection, or exploitation. This part rewards strategies that are currently performing better than average. It's a deterministic force that tends to reduce diversity by concentrating capital into the hands of the current winners. This is the survival of the fittest component, driving the market towards efficiency based on known information. The second force is innovation, or exploration. This part introduces randomness and pushes the system towards greater diversity. It prevents any single strategy from completely dominating the market forever and allows for adaptation to changing conditions. This is the, quote, mutation component, ensuring the system remains robust and can discover new, potentially superior strategies. So the evolution of financial strategies is a delicate dance between exploiting what works now and exploring what might work in the future. This equation provides a powerful mathematical framework for modeling that dynamic balance. Today, we have successfully broken down the Darwinian selection equation. We now understand how it models the evolution of financial strategies through a balance of performance-based selection and random innovation. Thank you for watching.